Our next speaker is Dr. Byron K. Lichtenberg, and he has flown 2 space shuttle missions as a payload specialist, representing over 100 scientists with experiments from all parts of the world. He's a retired Air Force pilot, flew 138 combat missions in Vietnam and earned 12 medals. In '84, he co-founded Payload Systems, a space service company, which flew the first commercial payload aboard the Soviet space station Mir. In 1991, Dr. Lichtenberg founded Omega Aerospace Incorporated, a company dedicated to the advancement of space travel for all people. He is also a member of the board of directors of the National Space Society. So we give you Dr. Byron K. Lichtenberg.
Thank you. It's nice to be here in this group of friends, and what I feel like I'm doing today is really preaching to the choir. But I think sometimes you have to hear things said that you probably know are true, but you're kind of afraid to stand up there and say them. As everybody has their own disclaimers, I'm going to put out a first couple of disclaimers, and the first one is that I'm not a NASA employee. I've never been a NASA employee. I'm also not into space shuttle bashing because, as you heard, the shuttle's kept this little body alive for 2 missions. So you're probably not going to hear a lot of bashing of the shuttle, but you're going to hear some things this morning that are examples of how the shuttle is run and operated that I think we need to change if we're ever going to do what Rick thinks we're going to do and what I believe we ought to do too, which is to get a lot of people into space and do it soon. What I'm going to do today is not a whole lot of technical things. I'm going to start out with probably an analogy that you've probably heard before, but I think it's important to set the stage. Analogy of looking at some other things in our history, like the airplane industry, and see how they got to where we are now, and how we can look back on those things, reflect on it, and use some of that knowledge to maybe get us to where we want to go in the future. I'm going to talk then a little bit about the shuttle and just give you a couple examples of some things that need to be fixed in whatever we do next, and then kind of end up with a kind of couple of ideas of what I think are important and where I think we ought to go. I also want to have another disclaimer that I'm not on McDonnell Douglas's payroll yet. And you're going to hear some things about the SSTO, the DCX program. Bill Galvez will come up later, and he can actually give you all the information. So you're not going to hear a whole lot of technical stuff from me because I'm not really in the middle of it. But there's some things I'd like to talk about. And with that kind of overview, let's jump right into it and start out with the airplane industry a little bit. Think back about 90 years ago, I guess, when we started flying our first airplane flights. And if you look at the progression of the airline industry, the first few years it was chaotic, I think was the word we just heard from Rick, and that's simply true. It was very chaotic. We had people going off. Everybody's out there trying to build a different kind of airplane, 1 wing, 2 wings, 3 wings, 1 engine, 2 engines, pusher engines, puller engines, all kinds of different concepts. And if you look at those early years, there was this myriad of designs out there. Everybody was trying to get out and do something, and of course the ones that tended to work best were the ones that got farther and faster, and they're the ones that we ended up going with. If you look at the role of the government in there, there wasn't a whole big role in the beginning, but as the industry became a little more structured, all of a sudden we realized that, hey, maybe these airplanes can be used for something like the military. We're about to go into a war, and all of a sudden the military people say, well, we think we can really make this thing useful for something. Where in the beginning everybody said, that's crazy, people shouldn't fly. Well, so we went through World War I, and of course that was really the beginning of the airplane industry, but at that point it was really used almost solely for military aspects, and a lot of the development was done by the government, so there was this kind of infrastructure thing going along. But the nice thing about it was that there were some crazy people out there, barnstormers and some other folks that took this technology and went out and did something with it. They went out to carnivals and eventually started selling rides, and we still hadn't developed any kind of a passenger industry at that point because it was still pretty risky. There were those few people out there that were willing to take some risks. They would go out, and in spite of all the airplane crashes and the problems with it, the delays, the uncertainties in the weather, uncertainties in the equipment, uncertainties about even where you're going to land once you take off, because you had no idea you're going to get to where you wanted to go, but just knew you're going for a ride somewhere. But there were people out there willing to do it, and as we got a little better, we still needed a lot of government help. We needed the subsidies for the airmail system to really put in place the infrastructure, the air traffic control folks, the airports, the beacons, the navigation aids, a lot of work with the airplanes themselves. And so there was a role there that the government played that I think was really necessary, because if you really had some infrastructure that had to be developed, and then you could go off and you could start doing some interesting things. You could start getting the cheap transportation, you get the reliable transportation. And I want to stress the word reliability, because you'll hear that throughout my talk this morning, because that's, I think it's really key. Well, let's move on to the space program now and look at some analogies. The space program started out initially as totally military. So people decided there were some things we could do with satellites in orbit, and we had all of our military rockets that were out there trying to pop things into orbit. And one day somebody said, maybe we put some people on there, and sure enough, that's what happened. But it was all military generated. There really wasn't any other push at that point. And the early generations of Mercury Gemini program really was built on the earlier intercontinental ballistic missiles. The first time we really got to a pure civilian design really was the Saturn V, when we were looking at going out and trying to get people to the moon, which was arguably a civilian program, but that was the first time that we really had generated something for civilian use. The shuttle came along next, and that was sort of mostly civilian, supposed to be, but as some of you might remember, in the early days, there was a lot of input from the military about the design of the shuttle system, just how it was supposed to work, what kinds of performance specifications it was going to have. Could it make a certain cross range? Could you take off and pop the satellite into orbit, come back and land before the bad guys could track you and figure out, what particular orbital parameters that satellite might be in? So they had a lot of performance requirements were put on the shuttle, which tended to add some weight, decrease the payload, so that there was still a lot of military influence, even in a fairly civilian program like the space shuttle. Well, that's kind of where we're at now, and it's taken quite a while. And the question is, in this analogy, well, where's the next step? Where do we go from here? What do we do now? How do we move this thing from being totally government to somewhat military oriented? How do we move this off into some sort of a commercial venture? And NASA had an office of commercial programs. It sounds great. There's been a lot of proposals made to NASA to try and do that. A couple of them that you're probably as familiar with as I am, but I'll reiterate them here. There was a plan back in this early middle 80s to have a public financing, or actually private financing, of a fifth space shuttle orbiter that would then be leased to NASA so that they could use it to help their traffic flows. And it could be also leased out to other people to do some very interesting entrepreneurial things. Well, what happened to that? NASA said, "No, we don't want private industry to come up with $2 billion to buy a shuttle, because then they would own it, and we wouldn't have control over it anymore. We don't need your $2 billion. Go away." Yeah, you might know who I'm referring to. Well, the next thought was, well, okay, if NASA wants to own these shuttles and they want to operate them, maybe a private company could rent one. That's kind of a novel thought, rent something from the government. So some folks got together and said, if we build a module that bolted into the payload bay that had some windows in it, we put a bunch of seats in there, maybe we could start doing some space tourism, get some people into space. So they put that idea together and got some little financing, went to NASA and said, okay, we're going to build our little scenic cruiser bus, and we want to bolt into the orbiter. How much would you charge us to go for a ride? What? We're not going to do that. You crazy? We're not going to take people in orbit. I mean, we've got our astronaut corps. I mean, we've already hired people to go into orbit. We're not going to take all these other folks out there. I could go on. John Denver went to him and said, well, okay, I just want to buy one seat. I'll pay you $1 million, I just want to go for a ride. How much does it cost? No, we can't do that either. I'm sorry. So John went to the Russians. You've probably heard that story. And they said, yeah, you can buy a seat, but it'll cost you $10 million or so. And he said, well, it's a little steep. So at least we've got a good idea where the price range is. Some elasticity here between $1 and $10 million. But clearly the shuttle really hasn't made it yet. So it's kind of discouraging, actually, because you look at me. I mean, you say, well, how did I get on there? I'm not sure right now. It's, if you look at the whole trend, I'm going to digress here for a second, but if you look at the whole trend of where payload specialists, people who have some things they want to do in space, but they're not necessarily NASA employees or haven't gone through the indoctrination of astronaut training per se out of Houston. Those folks are dwindling as we go down the road instead of increasing. And as the shuttle gets more and more reliable, it's up to 50-some missions now, and we think we have a good handle on it, people feel good, but if you look at it, what's happening, there's a contraction taking place instead of an expansion. And I guess I submit that 5 years after we returned to fly, after the Challenger accident, some 20-some, almost 30 flights later, we still haven't been able to fly a teacher in space that we committed to doing in about 1983. So I submit that we're not on the right track here. I just, I find it still hard to believe there are people out there that want to take that risk. I think there's a lot of people in this room. I'm not going to do it, but if I ask for a show of hands, I'll bet I couldn't see the back wall about who would be willing to take a risk to go fly in space. And I sort of felt that way, and I kind of feel like, NASA and their organization doesn't have the right to say, well, we're the only brave people, we're the only people around willing to take a risk. So anyway, that's my little homily on the shuttle. So I don't think that NASA is in the business of trying to push commercialization. They really are in a different business, and Rick made that same point just a few minutes ago. So let's get on to the subject which I'm going to talk about today, which is cheap access to space. And I'm going to do that by first taking a look at some of the shuttle ops and say, well, what kind of things can we learn from it? First, we know that the shuttle was initially planned, as you heard a few minutes ago, to launch 50 times a year. It was going to fly once a week. We're going to have a fleet of 5 orbiters. It was going to cost about $10 million to get into orbit. You could take, probably 50,000 pounds up there. So you have a cost somewhere around $200 a pound, which is pretty good. And of course, it never quite met those goals. But as Rick Chappell said earlier, just because you don't meet a goal doesn't mean the program wasn't successful. And I guess I'd like to submit to you that the shuttle really is a developmental program, and the goal was to make it the first DC-3, the first reusable vehicle that could go up and really open up this frontier. And Rick was absolutely right that to open a frontier you need transportation, and we don't have it yet. The actual operations, as you're probably aware of, are around 8 flights a year right now, and people do all kinds of strange things with numbers. If you take the total budget of the shuttle of about $4 billion a year and divide by 8, you get about $500 million a flight. Now, I don't think that's really the way to quantify how much it costs to go on the shuttle. Personally, I think you kind of need to look at marginal costs, but NASA never gives you those, so you really don't know what you're looking at in terms of cost. But anyway, I would say that it's pretty expensive. It's out of the range of most of us to write a check for that kind of thing. The orbiter, instead of doing a week turnaround, being able to fly once a week, now takes 2 to 4 months to get it turned around. And that's partly due to problems that happen with the Challenger. People are very conservative, although I do think that Bob Crippen and the folks at Kennedy Space Center are trying to make some rational steps in the direction of saying, hey, if we've just flown this thing and it's just come back and system X or Y or Z has worked great, why do we want to tear it apart, check every little piece individually, put it all back together again, and then test the hell out of it, make sure it works again? I mean, airline operations don't work that way. If you're going to have something that you fly up there and it works, then it works. Well, don't fix it, Keep on. So if you look at the shuttle main engine system, it's supposed to be reusable, but really the system is refurbishable. And there really is a difference there, and I think we need to make that difference. Reusability is much different than refurbishability. And if you're talking about basically taking the turbo pumps out after every flight, a total rebuild of the engines after every 3 flights or so, you get yourself into a situation where just the costs just go really right through the roof. That brings us to this whole issue. Well, we really didn't know, first of all, the operations cost of the shuttle. We really didn't know what it was like because we'd never done it before. So I guess I say that now that we've done it, we do know. We know those areas that drive up the cost. We know that we have a marching army on the ground, thousands of people on the ground to support a flight with 5 or 6 or 7 people in orbit for a week. And they're all looking at their screens, and they do a lot of processing and sometimes hand-wringing. But there are areas like this refurbishability that we've got to handle on. We say, okay, the next generation has got to do something different. We can't afford to have control centers of hundreds of people around the clock watching out for the vehicle. It's got to be much more autonomous. It's got to be able to take care of itself. It's got to be reliable. Some of the other examples of a typical mission that tend to drive the costs up, if you look at a shuttle flight, it's generally planned several years ahead of time. The crew members, if it's a kind of a generic shuttle mission, the astronauts are selected about a year ahead. If it's a science mission like the ones I was on, we were supposed to be selected a couple of years ahead, but if you kind of do some computation, you'll know that I've had 2 flights in 15 years, so a couple of years turns into quite a few years. Not to say it's not worth it, because it certainly is, and that's what I'm up here, because I know you all think it's worth it too, but it takes a long, long time, and it's a lot of commitment right now. The payloads, if you're going to put something in orbit with the shuttle, it needs to be delivered about a year ahead of time. It's got to go through all kinds of tests at Kennedy Space Center, be integrated and checked at all these different levels, and finally about 2 months before flight, it makes its way into the orbiter, and then it hangs around there for a while, it goes out to the launch pad and sits for about a month, and then you're finally really ready to go. So, you know, I guess the point there is that we need to be able to compress these times. We need to have something that we can bring a payload in to have a sort of a very standard set of interfaces that you can just pop in there and go, whether it's a set of seats, or whether it's a mechanism to pop out a satellite, or whether it's a cargo bin that you're going to go up and resupply some infrastructure that's up in space. When Krista McAuliffe was training, she was assigned about 6 months before the flight, so that the NASA folks figured it would probably take a minimum of about 6 months just to kind of get you checked out to be able to not hurt yourself on the shuttle and make sure you could work all the systems. And now after Challenger, we've got a lot more emergency things in there, so it takes even longer to understand how to work your parachutes and jump out of the poles and do all the things that are supposed to be able to save you in case of emergency. But it takes a long, long time, and I guess I would say that we've got to get that time down, that things shouldn't be that difficult to do, and we need to figure out ways to get around that. So where are we going? Well, take a look at the airlines for a second, and I think that there's where we really ought to try and go, and you're probably going to hear that in the SSDO, the DCX, the SSRT presentations, that you want to move more towards an airline type of operation. You really need reusability. I find it hard to believe people say, well, it's cheaper to build a rocket and fly it once and throw it away for $20 to $40 million. That's cheaper than it is to refurbish or reuse something. And I just don't have any figures, but all I can say is personally that doesn't seem to make a whole lot of sense when you're throwing away $30 to $40 million every time you go fly it. You also have the problem there of reliability, that every time you fly an expendable launch vehicle, as you know, it's the test flight every time. It's the first flight of a brand new vehicle, the first and last. So I guess I don't think that's the way to go either. How do we get reliability? Well, one of the ways you do it is you back off from the edge of the envelope. And the shuttle really had to kind of do edge of envelope things because we'd never done it before. We really didn't know how much this thing was finally going to weigh. We didn't know how much thrust we could get out of the engines. All we knew is we had to go for the very last bit of performance to assure that it was really going to get into space. And then we kind of lived with what we had. And that's why you have shuttle main engines now that are rated at 100%. And maybe you all can understand this, but they generally climb at 104 to 109% of rated thrust. So, you know, you're up there right at the very edge every time. You know, you don't hear a shuttle launch where they're flying at 95% of rated thrust. You know, that just doesn't happen. So they're pushing the edge of the performance envelope all the time. And I think that we need to step back a little bit if we're going to try and do cheap access to space and design something for 100%, check it there, but maybe fly it at 90%. This does a couple of things for you. It gives you an extended lifetime. If you look at the way the airlines operate, they don't go to maximum power on every takeoff. They have a setting. They say, well, if it's so many degrees, we need this much thrust, we have this many people on board, we need this much percent. And they just use as much as they need. If it's a longer runway, you pull the power back a little bit because you get a longer lifetime. It pays dividends in reliability. If you operate your system at something like that, now you've got some possibility of having an engine out capability where if you have things that are not working at totally 100% for normal ops, if you have an engine out problem or you get an emergency, you've got a little bit extra power that you can use, and that can get you out of trouble. That can give you intact abort capabilities. With a little bit of luck, it can give you an abort to orbit capability, which would be nice to have, but I don't think it's necessarily a design driver initially. We can get there a little bit later. Another issue that's important is operability and maintainability. And the shuttle was not really designed for that. I've crawled around inside it a little bit, and if you want to get in and, for example, replace one of their auxiliary power units, which is like a small jet engine that's used to power pumps to provide hydraulic power for the orbiter. It takes a bunch of work stands. You have to crawl in there. First you have to go in and make sure it's purged and that there are no toxic materials in there. And then you have to get an airflow, so you put some sensors in, and then you do little lights and get your booties on. And once you've got the outside work surfaces put around, then you open the back and you kind of crawl in, and you have to put little workstations in as you go, and it's kind of like crawling on these catwalks to get in there, and you almost have to be a contortionist. And I really take off my hat to all the technicians at Kennedy Space Center that get in and do those things, even when the thing is up on the pad vertically. It's incredibly complex and very densely packed in there, so it wasn't ever really designed to be maintained. So that we really need to look at anything, the litmus test of any next generation vehicle, I think, needs to be reusability, operability, and maintainability. Another area is autonomous operations. I touched on that earlier. If we have this marching army of people in control centers and everybody's staring at scopes and things, we're never, ever going to be able to get the cost down. The shuttle is pretty much controlled. I say controlled, it's monitored on the ground. There's a lot of uplink commands. There are a lot of periods of time when the crews are asleep, and it's controlled directly from the ground. We have made a few strides, I would hope, in computer power since the early 70s. In fact, if you think about the shuttle design, it was designed in the 70s, but based on 60s technology, and they've got computers that are about the size of this lectern that hold a whole 256K of memory. So I submit that Rick's computer that he used for his talk is probably a reasonable alternative for those general purpose computers that the shuttle uses. So there are some improvements we can make. You know, it's not all bleak and doom, and there are ways that we can that I think we can get there. Well, how do we do that? Again, as I said earlier, disclaimer is that I'm not out here to sell any particular program, but I've got to admit a certain fascination for single stage to orbit, and I make a caveat there. It's not just single stage to orbit, but it's reusable single stage to orbit. And there's a lot of controversy about that. Some of the rocket scientists in the room will say, well, you have a terrible mass fraction. You get very, very little payload in orbit because most of your weight is structure and fuel. And yeah, that is true. But I think what we need to do is start looking at some different performance specifications and not try to, for example, maximize the amount of payload weight, but we need to minimize the cost, minimize the time, and maximize the reliability. And if you want more payload, you either build a bigger vehicle, for example, or you fly two of them. I mean, there are a lot of trade-offs you can make here. There are other options. Again, I would say that any option that would have to pass my test would have to stand up to reusability. The two-stage orbit vehicle seems to make some of the rocket scientists happier because then you can get a larger fraction of your mass for your payload. A larger fraction of the whole vehicle can be payload to get in orbit. And that's fine. I mean, I'm not against two-stage orbit vehicles. In fact, Boeing came out this week. Bob Truex has a Sea Dragon. There's a variety of concepts around. But I would say that, you know, we're still looking at view graphs. And if you take a look at the DCX, the SSRT program, you're looking at real hardware. So I put some faith in actually flying something, going out and doing something, rather than just doing some view graph engineering. If you're doing a two-stage orbit vehicle, you've got to design and develop two separate, totally different vehicles. And a lot of the concepts that you see out there would use an air-breathing first stage with wings and things, and that's good, but we really don't have much of that unless you can get the Concorde, which can't carry much, or maybe the Soviet Tupolev, the supersonic thing, or maybe we've got some other programs around that are doing hypersonics, but stuff that really hasn't come to the forefront yet. There's really nothing out there, and if you read that article in Aviation Week about the Boeing proposal, and I love Boeing, but they said, well, this is all ready to go, it's off-the-shelf stuff. All we need to do is develop a 74,000-pound class turbojet engine. That's all we need to do, and we can get up to Mach 3, and then we can pop this little rocket ship off the top of it, and we'll have two-stage orbit, and everything will be great. So I guess I would say go for it. And again, you know, looking at different options. I'm not here to say we need vertical takeoff, vertical landing, single-stage orbit, but what we need is a variety of options, and that's the way I think we really want to go. The last thing, I guess, to talk about is kind of this whole philosophy of re-examining things. You've heard it in a couple talks already this morning. The fact that we sit here and we wring our hands and we say, well, golly, what should we do? And every year we go up and come up with a new set of plans. And We've looked at the space station program 10 years, and we've developed a whole lot of paperwork. And I don't know, I get frustrated, probably like a lot of you, that it's time to go out and start building some things. And let's take a look for a second at flying some things. And okay, maybe we don't get to orbit with a really useful payload the first time we do it. I think we need to do this incremental program to get up there. The way that they're setting up the DCX program to go up and do an initial series of prototype flights seems to make a lot of sense to me. The second stage would be to go ahead and build a full-scale vehicle. Okay, we might not make it to orbit first, but you might get to Mach 15 or 20. You go incrementally, so you learn what's going on at each particular stage. You get a feeling for it. As more materials, more propulsion becomes available. I think that we've already seen a lot of spin-off from the NAS program. You're getting better materials, higher performance and lower weight, so that the things are coming out of programs that, again, NASA hasn't flown anything, but the research is out there to give us some materials that can be used in programs that might be able to fly pretty soon. I'm an old Air Force pilot, and back in the old days when the jets weren't all that powerful and they wanted to carry a little more payload, they'd strap on a couple of JATO, Jet Assisted Takeoff bottles on the side. So it's sort of like a first stage. So, you know, there's certainly nothing wrong with saying, okay, you want a few more pounds into orbit on this particular mission? Maybe you want to strap on a couple of small throwaways. It's sizing, and it's trying to figure out what you're designing to. And again, I would like to go back and say that the design parameters that I see are reliability, performance, operability, or not performance, but reliability, reusability, operability, and maintainability. And I think we're going to get there. The question is, what can we all do about it? Well, you can get and stay active. You can get involved with your congressmen, congresswomen, the Congress critters, I guess they call them, senators, legislators. Legislators is probably the best word. Let them know how you feel. You can be active. You can write letters of support. You can read, find out about things. You can spread the gospel to some of your friends and try and get them involved. And since I am on the board of directors, you can get your friends to join NSS and Space Cause and Space PAC, and you can go ahead and be active. Another thing you do is kind of keep the faith. I think that things are going to happen out there, and I think that it's not going to be inside of NASA, it's going to be outside, and that means that it's going to probably involve a lot more of us than it would have initially. And finally, I guess, you say, well, why am I pushing that? Well, I've flown 2 space shuttle flights, and I've been a passenger going up, but I've got a lot of hours as a pilot, and when we go up there, I'd like to be your pilot and take you all up there. So thanks, and we'll